Suppose we have a triangle here with an in radius r, and the radii of the three x circles are Ra, Rb, and Rc. The lengths of the sides of the triangle are A, B, and C. The angles of the triangle are alpha, beta, and gamma, and S is the semiperimeter, which we know equals the distance between this vertex of the triangle and this tangency point of the x circle. With big S, we're going to denote the area of the triangle. We're going to see how we can express all these quantities as products of sines and cosines of alpha, beta, and gamma, and the circumradius big R of the triangle. Let's go through the list one at a time. First R, the in radius. We have that the distance between this vertex of the triangle and the incenter, if we call it x, we know that it equals 4 times r sine of alpha over 2 sine of beta over 2. Furthermore, we know that this angle is gamma over 2 because this is an angle bisector of this angle, and we know that this angle here is 90 degrees, where this is the point of tangency of this circle and this line. Then, from this right angled triangle, we get that r equals x times the sine of gamma over 2. And from this and this, we conclude that r equals 4 times big R sine of alpha over 2, sine of beta over 2, sine of gamma over 2. Now let's try to find the expression for S, the semiperimeter. We know that if this is our triangle, and this is one of its x circles, then the distance from this point to this tangency point is S. Let this point be the center of the x circle, and therefore this here is the angle bisector of this angle, and so this angle equals gamma over 2. And also, we know that this line is the angle bisector of this angle here, or the external angle bisector of this angle here, and so this angle equals 90 minus beta over 2. And now we get that this angle is alpha over 2, such that the sum of the angles in this triangle is 180 degrees. Let this length here be x. From the law of sines, we know that this side of the triangle equals 2 times r sine of alpha. Now we can apply the law of sines for this triangle, and we can express x in terms of 2r sine of alpha. So x equals 2r sine of alpha times the sine of this angle divided by the sine of this angle. So we get 2r sine of alpha times sine of 90 plus beta over 2, which is this angle, divided by sine of alpha over 2, which is this angle. But we know that sine of 90 plus beta over 2 equals sine of 90 minus beta over 2, which equals cosine of beta over 2. And we also know that sine of alpha equals 2 times sine of alpha over 2 cosine of alpha over 2. So we can cancel out the sine of alpha over 2, and we get 4 times r cosine of alpha over 2 cosine of beta over 2 for x. Now consider this right-angled triangle with hypotenuse x and angle gamma over 2 here. We get that this segment, which is S, equals x times the cosine of gamma over 2. And so S equals x times cosine of gamma over 2, and therefore S equals 4 times r cosine alpha over 2 cosine beta over 2 cosine gamma over 2. Note that we can find RC, the radius of this circle, by using the same right-angled triangle we used to find S. It is a right-angled triangle with hypotenuse x, and this angle is gamma over 2, and so RC equals x times sine of gamma over 2. And now that we got this, we can replace x with this expression, and we get that RC equals 4 times r cosine of alpha over 2, cosine of beta over 2, and sine of gamma over 2. Similarly, we can find the expressions for the other two radii of x circles of the triangle. Instead of putting the sine in the gamma part of the expression, we can put it in the beta part of the expression for Rb and in the alpha part of the expression for Ra. The rest are all cosines. If you consider the sum of the angles in this triangle, you're going to see it's 90 plus gamma over 2 plus alpha over 2 plus this angle, and so this angle must be beta over 2. And so S minus A equals RC times sine of beta over 2 divided by cosine of beta over 2. So we get this. And now we can replace RC with this expression, and then we get S minus A equals 4 times r cosine alpha over 2 from here. And then instead of cosine beta over 2, we write sine of beta over 2, because cosine beta over 2 cancels out here, and the sine of beta over 2 goes here, and then sine of gamma over 2, which comes from here. Similarly, we can find expressions for semiperimeter minus b and semiperimeter minus c. We again have two sines and one cosine in the expression, but instead of putting the cosine at the angle alpha in S minus a, we're going to put the cosine at the angle beta in S minus b, and the cosine at the angle gamma at S minus c. And this is how we get all these formulas. Finally, for the area of the triangle S, we know that it equals a times b times sine of gamma divided by 2. And a and b we can replace by 2 times r sine of alpha and 2 times r sine of beta, so we get this expression, 2r squared sine of alpha sine of beta sine of gamma. But we can replace sine of alpha with 2 times sine of alpha over 2 cosine alpha over 2, sine of beta with 2 times sine of beta over 2 cosine beta over 2, and sine of gamma with 2 times sine of gamma over 2 cosine of gamma over 2. So we get this expression here. 16r squared, the product of the sines of the half angles times the product of the cosines of the half angles. And from here, it's really easy to see that S is actually the product of little r times the semiperimeter. When we multiply this and this, we get 16 times r squared times the product of the sines times the product of the cosines, which equals this. It's also easy to see that S equals S minus A times RA, because we again get 4 times R times 4 times R is 16R squared, and then cosine alpha over 2, cosine beta over 2, cosine gamma over 2 from here, and sine beta over 2, sine gamma over 2, and sine alpha over 2 from here. Similarly, S equals S minus B times RB and S minus C times RC. This result is written here. And now we can get even more interesting identities by considering what S is, the semiperimeter, and what S minus A, S minus B, and S minus C are. Because you see, S equals A plus B plus C divided by 2, which can be written as a sum of sines. We have that S equals 4R cosine alpha over 2 cosine beta over 2 cosine gamma over 2. On the other hand, S equals A plus B plus C over 2, which is R times sine of alpha plus sine of beta plus sine of gamma because of the law of sines. And when we cancel out the R here and here, we get this equality, which states that the sum of the sines of the three angles in a triangle equals 4 times the product of the cosines of the half angles in the triangle. Similarly, if we consider S minus C, we know that it equals 4 times R sine alpha over 2 sine beta over 2 cosine gamma over 2, but it also equals A plus B minus C over 2, and the law of sines allows us to rewrite that as R times sine alpha plus sine beta minus sine gamma. And when we cancel out the R here and here, we get the following identity. Sine alpha plus sine beta minus sine gamma equals 4 times sine of alpha over 2 sine of beta over 2 cosine of gamma over 2. Similarly, by considering S minus B and S minus A, we get these two identities here. This is the optional problem. We need to write this expression 4 sine alpha over 2 sine beta over 2 sine gamma over 2 as a sum. And then we need to find the geometric meaning of the identity we got. And here's the solution. The expression we have can be written like this. And then take this expression in the parentheses. We can apply the formula sine times sine to this expression, and then we get cosine of the difference of the angles beta minus gamma divided by 2 minus cosine of the sum of the angles beta plus gamma divided by 2, and the 2 cancels out with the 1/2 in the formula, so we get this expression here. We know that sine of alpha over 2 equals cosine of beta plus gamma over 2, because the sum of alpha over 2, beta over 2, and gamma over 2 is 90 degrees, and therefore we get this expression here. It equals 2 times cosine of beta plus gamma over 2 cosine of beta minus gamma over 2 written here, and then minus 2 times cosine squared of beta plus gamma over 2, which is written here. And now we can apply the formula for cosine times cosine here, and then the 1/2 cancels out with the 2, and then we get the cosine of the sum of this angle and this angle, which is beta, plus the cosine of the difference between this angle and this angle, which is gamma. And so we get cosine beta plus cosine gamma from here. And from here, we first write cosine of beta plus gamma over 2 as sine of alpha over 2, just like we did here. And then we add and subtract 1, as given here, and then we group this in parentheses. The expression in the parentheses equals cosine of alpha, because of the formula for cosine 2 alpha equals 1 minus 2 times sine squared of alpha. So finally, for our expression, we got that it equals cosine alpha plus cosine beta plus cosine gamma minus 1. For the geometric interpretation, it's a good idea to take this equality and multiply both sides by the circumradius big R. Then this left-hand side equals this, which is small r, the in radius, and this right-hand side becomes r cosine alpha plus r cosine beta plus r cosine gamma minus r. This can be rewritten as small r plus big R equals r cosine alpha plus r cosine beta plus r cosine gamma. Take a look at this picture. This point here is the circumcenter of the triangle, so the center of this circumcircle, and this point here is the incenter. And so this equals this equals this equals the radius of the incircle, small r, and this equals this equals this equals the radius of the circumcircle, big R. The sum of small r and big R, according to this formula, equals r cosine alpha plus r cosine beta plus r cosine gamma. But we know that if we drop perpendiculars from the circumcenter of the triangle to each of the three sides, then their respective lengths are r cosine alpha, r cosine beta, and r cosine gamma. And therefore, the geometric fact that we got is that the sum of the in radius and the circumradius of the triangle equals the sum of the perpendiculars dropped from the circumcenter to the three sides of the triangle.